Hello, I'm a.c.atkinson.
And I'm Marco Riani.
So we're going to continue looking at some of the content of what we think of as our exciting new book about robust regression, which we have written together with three further co-authors. Today we will continue to look at examples of non-parametric regression. For those of you who are following this on the book, we are in section 7.6, and we start with an example of some synthetic data used by Wang and Murphy to illustrate the properties of AVAS.
There are 200 observations and 4 explanatory variables, all independently uniformly distributed on the interval -1 and 1. That's the linear model. Then what we do, we take the log and then we put 9 outliers. So let us go to the code. Here we have used a particular seed, and then this our routine MTR generates the same random number as those that come out from R language. So you can easily reproduce them in R using this seed. And then we have some contamination. Just to give you an idea of the y-x plot, here it is.
I think any data analyst confronted with this plot will be somewhat confused as to where to start.
Let us call our routine for automatic model selection. Show the results of our best model, and here it is. So the best model contains all options part 1, apart from the trapezoid. Differently from what we have seen before, notice that the value of the 4 statistics here are visualized as bars. We put show bars is equal to false, then we can visualize this plot without bars. Let us see in a greater detail what these 4 bars are.
In general, the number of outliers detected is k. From left to right, the bars give the values r squared, n minus 2k over n, and significance point of the Durbin-Watson statistic for correlation between the residuals, and the significance level of the test of normality using the 3rd and 4th moments of the residual.
So the p-value of these 2 tests is much greater than 0.05, so the first solution is fine. Now we extract the best solution and we see the result of the best solution.
It is clear from the left-hand plot that we have got a nice smooth transformation of the response, and in the right-hand panel of the left-hand plot we have a clear distinction between the added outliers and the band of residuals, which shows pretty constant variance along its length. Much more interesting, I think, from a statistical point of view, are the other plots, which are the transformed values of the explanatory variables. X1 is a nice sinusoidal shape, but X2 is probably really the most interesting. If you look back at the model, you will see that this explanatory variable is the absolute values of X2 minus a constant. What we have used to fit the models is smoothing, and you might expect that by using smoothing we would get rounded curves, but in fact at the bottom here, the minimum of X2 is commendably sharp.
That concludes the analysis of this data. Now we move to another example, which is the prediction of the weight of fish. The data can be found in this website. The sample size is 159.
So the response is the weight of the fish in grams, and the 3 explanatory variables are all to do with really the length of the fish. It's the length from the nose to the beginning of the tail, the length of the nose to the notch of the tail, and the length of the nose to the end of the tail. After the deletion of the data on Pike, 142 observations remain. Scatter plots of the responses against the three explanatory variables reveal that all three lengths are, as one would expect, highly correlated with the response and with each other. So we can expect to find some problems that occur in regression with collinear explanatory variables.
We start by our automatic model selection procedure. Note that in this case we impose a monotonicity constraint on the transformation of the explanatory variables. Now we run the automatic variable selection procedure and we impose a monotonicity constraint.
What we would expect is that the weight of the fish would increase with the increases in the lengths of the three explanatory variables. So the monotonicity constraint is entirely reasonable.
Let us see the solutions that are found, and here on the right we have the heat map among the different solutions. And then the correlation coefficient among the different solutions is very, very high. This plot on the left has a slight instability, as we commented before, due to the correlation among the explanatory variables.
And what you mean by instability is that if you run the data again and again, you don't get entirely exactly the same plot.
Exactly. Now we concentrate on the first solutions, which has very high values of the first three statistics. Now we see the detail of the best solution. We find three outlying observations.
You'll notice that in the right-hand panel there is an extreme outline down there at the bottom. This is the one that we commented on before when we were looking at the data.
And then two other outliers.
Yes. Okay.
So now we restrict to considering just the first explanatory variable. Now we compare the solution coming from the analysis of using all explanatory variable and the one which is uses just one explanatory variable.
What we have here in thinking about the data is we have the weight and we have some lengths. And when the weight is a measure, of course, of the volume of the fish. And in this kind, if you think about dimensional analysis of data, we could expect that the weight should be transformed to the 1/3 to give all four variables in the equation the unit of length.
In fact, if you have just one explanatory variable, you can see that the agreement with 1/3 is pretty good.
Although the agreement when you have the three explanatory variables is less good but not bad.
Now we move to another example, so-called internet marketing data, taken from this R package. There are three explanatory variables, are the budgets for advertising on three channels, YouTube, Facebook and newspapers. The response is sales. We start loading the data and analyzing as before the y-x plot. The y-x plot is not given in the book, but we simply comment it just to say that there is a strong relationship between the amount of advertisement on YouTube and the sales, and also on Facebook. A fit regression model based on the original data, and then we notice that the F statistic of the significance of the overall model is 504.
However, the T statistic for X3 only has a value of 0.658.
Here is the value of the T statistic. When we apply our traditional EVAs, we end up with the value of the F statistic which is even smaller than the value of the F statistic for the original model. The original model, the value of the F statistic was 504.
Whereas now, for this AVAS model, it's 472.
Now we apply our AVAS procedure, but this time with all options set to true. We find a set of outlying observations. Here we'll also impose the monotonicity constraints because it has a marketing interpretation. The p-value of the Darwin-Watson and the normality test are very small. And in fact, if you look carefully here at the top right panel, you can see that there is a pattern in the residuals. And this is reflected by the small p-values of the Darwin-Watson and the normality test. Now we check the F statistic, the value of the F statistic, which comes out after excluding the outliers, which is 936. Probably the linear model here is not enough to understand the non-linear relationship between the explanatory variables and the response. So we try a quadratic model. So we see we have the quadratic terms and the interaction terms. We run our automatic model selection procedure, and the best model has an R-square which is very high. Darwin-Watson statistic says that now the residuals do not suffer from autocorrelation, and the Jarque-Bera test is close to being significant. So the best model has 3 options, including robustness. And once again, this confirms that there are outliers in this data. Now, this is the output from the robust fit. This is figure and 723. Here we find just one unit as outlying.
So we would now like to compare this robust analysis using a quadratic model with non-robust analysis.
Now we run the AVAS using the quadratic model, just standard AVAS. And now we look at the value of the F statistic, which is 556, a value which is hardly better than the regression on the first order model without transformation of the response or of the explanatory variables. So despite we have a very complicated model, the gain is negligible. And now if we look at the output from the standard AVAS, the quadratic model, we find very disappointing results, in the sense that the plot of residuals against fitted values reveals that there is a typical strange pattern that we already commented.
Yes, these strange patterns are nearly always quite diagonal, aren't they?
Yes.
Yeah.
Yes.
Well, it's not really at all clear to us, I regret, as to what this is caused by. There must be somewhere something that the model is not adapting to.
Not that on the other end, in our robust model, after removing the outliers, we didn't have it at all.
Yes. A further analysis would be, of course, to highlight, to brush the outliers from RAVAS when looking at this non-robust solution and see if they give us any information about the behavior of the algorithm, but we will not dwell on this now.
Thank you for watching this video, and see you.
See you on some other subject soon.
Okay, bye-bye.